So maybe we should start, even though there is no clock. I think it's about time. So we're very pleased to have for our colloquium today Mike Zieve from University of Michigan, who will talk on his joint work with many people, one of whom, at least one of whom, to my knowledge, is here. And the talk is about the functional equation at composed of speech decomposed to state.
Thank you. I really want to thank Sam. I've never been treated so well in invited places. It's great. I'm not used to it.
Doesn't that make you suspicious?
I'm just kind of blown away. Anyway, so all these people, well, all except for, oh, wow, I have a laser pointer. That's true. Oh. Everyone except for Ben Weiss was an undergrad when I worked with them. Some of them have stopped being undergrads now. But, right, so I want to talk about this functional equation and show connections to lots of things. So, just to start with, so the functional equation seems like the simplest you could be. Like, just compose two things together and get the same as you.
Well, what are the things?
Ah, yeah, that's a problem. I want to be big on that. But just to show that you can make it even simpler, you can make two of the things be equal and one of them be x plus 1. So this is Abel's functional equation where, okay, so what are p and q? Well, they should be analytic functions. And this has been, I mean, Abel's paper was 1826. I mean, this is just some history to show that there's, to give you some sense of what's been done. So the Schrader functional equation, one of the functions, f is a constant times x, and again, p equals g. And understanding this with p and q being functions which fix 0 and which are analytic in some neighborhood of 0. Solving this was this huge question in complex dynamics that Gatto's, I mean, part of Gatto's Fields medal was for his work on this. And there are many great works in between. And then in some sense, I mean, one quite general thing in this direction was commuting rational functions. So in the early 1920s, Batu, Julia, and Ritt wrote, each of them wrote a long paper, and like Ritt's was the short one. Ritt's was only 50 pages. On what can you say about commuting rational functions? And I have to say that even today, it's not really satisfactory, the statement of the answer. Because the statement of the answer is very satisfactory unless f and g have a common iterate. But if f and g have some common iterate, I mean, so Batu and Julia could say nothing in that case. Even today, as far as I understand, the techniques of modern complex dynamics still can say nothing in the situation of a common iterate.
What does that mean, common iterate?
Some iterate of f is equal to some iterate of g. Usually, in all the papers I've seen, that's just excluded at the very beginning as a hypothesis, and then people go from there. And everything else can be done with the techniques, modern techniques of dynamics. Ritt was able, with algebraic methods, to give a procedure for kind of describing all solutions. I mean, in some sense, he did everything, but I can't imagine any situation where you could use his description to do anything else. I mean, and this has come up in several times in recent years, people have run into this, and they needed somebody that isn't exactly the answer that Rick gave. They need some consequence, and they can't get it. Because his description is just, it's not useful, although, I mean, what he did is, it's the only thing that's ever been done, straight. Anyway, and then many more. So this is just to give you a quick 2-minute history of the topic. There are lots of cases of this that have been studied. One that I can tell you, if you consider rational functions, you have polynomials, then Ritt did everything. And this was just tremendous. So Ritt explicitly described all polynomial solutions to this functional equation. But even today, we have just no hope of doing, at this moment, we have no hope of doing the same thing for rational functions. We would dearly love to be able to do so, but there's been a lot of work over the 80 years in between. And it was kind of building in one direction, and the pinnacle, at least in the public literature, or in the published literature, I should say, is keeping f and g being polynomials, but allowing these right guys, p and q, to be Laurent polynomials. So allow them to be rational functions with denominator of power of x. And that's...
Clarify the solution of these functions are given in the equation and which are unknown.
We want to write down a list of all
So all are unknown.
Yeah. And so what I'm going to describe today is an advance on this. We still need f and g to be polynomial, but now we can let
Or you want f not equals g and p not equals q.
Well, I'm including that as well. Because that is an interesting case. I mean, well, okay, that's a trivial case. But if f equals g, that's interesting. Like to say, when can f of p equal f of q? That's an interesting equation. And that's actually something we'll need to solve. But what I'll show today is all solutions where f and g are polynomials and p and q are rational functions. So that's quite a bit beyond what's done before. And actually, we can generalize. Instead of p and q being rational functions, we can let them be meromorphic functions on the complex line. So I'll show how and we really did choose this of co-authors from the previous, well, we'll go back, but we have a solution to this, and I'll give consequences to the various different consequences of this and the special cases of it to the various different other areas of math that I mentioned. Okay, so first let me mention that, well, for the purposes of this talk, I think this is the oldest result of the work that I'm pretending is modern work. This is the oldest modern work. So this is joined with Dragos Gioka and Tom Tucker. We had a 2008 Vecchioni's paper and a 2012 paper from Duke. And the question that we're asking is, if you have two complex polynomials, and you take the orbits of two complex numbers under them, so just alpha, f of alpha, f of f of alpha, and so on, and beta, g of beta, g of g of beta, and so on, when can these orbits have infinite intersection? So that was the question that we looked at, and we showed that if this happens, then the two polynomials have a common iterate. And it's sort of, so by a common iterate, I mean exactly what I said before, that some f of f is equal to g of g of g. Maybe a different number of times, different number of f's, different number of g's.
So it's if and only if.
Yes. Yeah, it's if and only, right, exactly. I need to make sure that I just ruled out, if you say it the right way, if you stated that there exists alpha beta, if you chose an alpha that was like a periodic one for f, then it wouldn't be, obviously wouldn't be true. But if you pick some f and g that have a common iterate, you pick any alpha that has an infinite orbit under under f, then you're done, because then the orbit of it under the common iterate is contained in its orbit under f and under g. Right. And this is an aside that Rit did this too. Rit went further and named all polynomials that have a common iterate. In the polynomial case, it's beautiful. Because it's kind of, well, it's mostly rational functions are just hard. There's all kinds of other examples. In the polynomial case, essentially for f and g to have a common iterate, they should both be iterates of the same basic thing. The only issue is there might be a linear that commutes, or sort of almost commutes with one of the things. Like sometimes you can stick like x cubed and negative x cubed have the same second iterate. Because negative x commuted with x cubed and then composed with itself to just be an entity. So up to some little things involving linears, the conclusion is really that f and g are both iterates.
So something about the English before you change it. You want to go to f and g have a common iterate. When do f and g have a common iterate? So the statement, f and g have a common iterate if there's an alpha and a beta and c with that property.
Yes. Well, that's if and only if also.
I'm just asking about that one. Because the English way of writing it there is you put the alpha beta first. So it's not clear to me what it's trying to mean.
I say if the orbits have infinite intersection, then
given f and g, if there exists alpha and beta with that property, then they have common iterate. That's the beta.
I think that works.
Well, that's just not the way I'm not sure what English means at all. I'm just thinking.
Anyway, okay. So at first you look at this and there's no functional equation. So the first thing we have to do is get a functional equation. So I'm going to give you the proof on the rest of this slide. And so why do we have two papers? Well, the behavior is completely different if the degrees of f and g have a common power. Like that's where you can get f and g to have a common iterate. Then that was the 2008 paper. And if the degrees of f and g have no common power, you really need different techniques, and that's the 2012 paper. Okay, so so the rest of the slide will be the proof. So how do we do this? We'll write f to the k for the kth iterate, And the original equation just says that fk of alpha, there are infinitely many pairs KL, so that fk of alpha equals GL of beta. Okay, that's true. So now comes some work. So this is the crucial observation, that what this means is that the equation, if you fix n and m, you look at this equation fm of x equals gn of y, you're getting for free infinitely many solutions to each such equation. Just move back, move k down by m, and move l down by n. Now you might worry a little. It's reasonable to worry that that maybe the k's are bounded, but they can't be, because all the fk of alphas for different k's have to be distinct. Because as soon as you get a repetition, you'll keep repeating, and the orbit will just be finite. So you couldn't possibly have had infinite intersection of orbits. Okay, so all the k's are distinct from each other, all the l's are. So actually, these infinitely many pairs include infinitely many pairs with both k and l bigger than any given bound. So we really do get this. For any fixed n and m, this equation has infinitely many solutions in this orbit. Why is that important? Well, that's important because the orbit is contained in a nice arithmetic ring. An arithmetically nice ring, I should say. So every fi of alpha, this is f of alpha, where does it live? It's like, well, it wants to be an integer. And the only things that make it fail to be an integer are alpha and the coefficients of f. Right? So if you have alpha and the coefficients of f, then all these f of alphas are gotten by them by just kind of integer polynomial relations in alpha and the coefficients of f. And likewise for g and beta. So we have finitely many things here. There's alpha and beta, that's 2. The coefficients of f and g, that's still finitely many. So there's some finitely generated ring which includes all of these things. So this equation has infinitely many solutions in this finitely generated ring. And then there's a hammer. So then Ziegel's theorem. Well, Ziegel proved this for the integers length generalized to a finitely generated ring. Says as soon as you have the situation, as soon as you have some equation in two variables that has infinitely many solutions in some finitely generated ring, it has to have a family of solutions parameterized by Laurent polynomials. So this equation, fm of x equals gn of y, the fact that it has infinitely many solutions in R implies that it has a solution in non-constant Laurent polynomials. So this is not the usual statement of Ziegel's theorem. The usual statement of Ziegel is that a curve with infinitely many integral points has genus 0 and most 2 points of infinity. But genus 0 just means that you're parameterized by rational functions. And at most 2 points of infinity means those rational functions have at most 2 poles. So you can make them be Laurent polynomials. You might have to do a change of variables, like maybe the poles were quadratic conjugates and merged over the rational, so that's why you can't necessarily get a solution with Laurent polynomials over Q. You might need to move to a quadratic field to include the pole, but that's fine. My whole point was just to get a functional equation, and we've got that. In fact, we have infinitely many. For every m and n now, we have another functional equation. So then the next step is to, here I'm hiding a lot of them, but so you solve each of these functional equations separately, and then you piece together the solutions. And the piecing together is really painful, because you get a lot of solutions to each individual equation which won't be solutions, which won't be compatible with each other. So to piece them together, we had to prove a totally separate result, which is different, which is joined with Peter Mueller, which says that if you have a large number of iterate of a polynomial, it says it can't keep decomposing into essentially new ways. So if you want to find all the decompositions of the 1,000th iterate of like a degree 32 polynomial, well, it's enough to just decompose the 5th iterate, and then all decompositions of the 1,000th are gotten by just sticking a bunch of f's on the outside. Okay, so and what we proved is that when you have a degree n polynomial that's not x to the n or Chebyshev, or negative Chebyshev, then once you've decomposed its log base 2 of n iterate, you know all decompositions of every iterate beyond.
What was this point about sticking f's on the outside? Except for that sentence, I understood what you just said.
Well, because if you
have all the factors occur at a fixed level, right?
Right. So if you've written f to the k is like a composed of p, then f to the k plus 10 is like f k composed of k.
The value. Yeah.
And what I'm saying is that every decomposition of a big number 1 looks like this, where the a and the b are coming from, at worst, the log base 2 of the degree. And this...
Oh, wait. So f to the k plus 10 already has a form. F to the k composes f to the k.
Right, but it's possible that f to the k plus 10 might have a decomposition that's not like this. That's
all
like some
decompositions
weird
are in
mix.
that form.
Right, exactly. Right. So once you decompose, like if you have a degree 256 polynomial, if you found all decompositions of the 8th iterate, all decompositions of 9th, 10th, 11th are gotten by just, there's no more internal mixing that can happen. This is really a result about, I mean, so x to the n in Chebyshev, like x to the 6th is x squared composed with x cubed, and those things commute. So when you decompose its iterates, you can put all the x squareds and all the x cubed anywhere you like. This is saying if you're not x to the n or Chebyshev, you can still kind of mix up the internals somewhat, but we control exactly how much you can. Okay. But anyway, so that, I mean, before we faced that question, I thought that Rick had done everything that could be done with polynomials. But that one actually didn't follow from his results, so that was painful. But anyway, but that's a separate issue. But anyway, then you do a little work and you get the answer. So that's
question. So this works regardless on the degrees of f and g.
as long as they're not 1.
Because you mentioned previous work only if degrees are.
That everything today is arbitrary. I think I should say what goes wrong with 1. What goes wrong with degree 1 is x plus 1. Like the orbit of 1 under x plus 1 is 1, 2, 3, 4, 5. It's all positive integers. And you can, take x squared plus 17 for your other polynomial and take the orbit of 3. It's some kind of strange looking thing, but it's contained in the orbit of 1. So you get infinite intersection with no common iterate. So and that's a common theme in this type of subject, that when you have an additive, like, things with an additive relation like that, just, well, they need to be avoided. Like, I'll get to that in a couple of slides. Okay, so that's the result, and that's the proof, and then there's the moral is at the bottom. By translating from the dynamics question into a number theory question, and you can use the number theory result to get back to a functional equation, and then solve it. And later in the talk, I'll explain how we actually solve functional equations. But let me say a little bit more about why this dynamics result is really kind of a number theory result. So that's the result. So let me reformulate this result. So I want to say this is really a two-dimensional theorem in disguise. So what am I saying? Instead of pairs, so that fm of alpha, gn of beta. So saying that fm of alpha equals gn of beta is the same as saying that the point with x equal fm of beta alpha, y equals gn of beta lies on the diagonal. And okay, so what we got was that f and g have a common iterates. There's some f to the I is equal to g to the j. Say like f to the 5th is equal to g to the 7th or something. But once you get that, then also f to the 10th is equal to g to the 14th. Like there's a whole, the minimal pairs so that this iterate of f equals this iterate of g, then all multiples of that are also still the same. And then you can just sort of mod out by 5 and say, like, if you just find the smallest pairs, the pairs with m smaller than the place where they start having common iterates, find the small pairs where they became equal, and then you get a whole arithmetic progression. Like you'll be able to take integer multiples of the minimal pair of mn that got them equal, and any integer multiple of that plus any spot where they actually happen to randomly equal each other will also be included in the set. Okay, so just a different formulation of the result is that the set of these pairs consists of finitely many sort of one-sided arithmetic progressions, if you will. Just some pair of integers plus all positive integer multiples of some other pair. Okay, so once it's reformulated this way, it starts to look like the Mordell-Lane conjecture, which is the theorem of Faltings-Goya. And so one formulation of Mordell-Lane is that if you start with a Mendelian variety, so just some nice group variety, an algebraic group that doesn't have any copies of the additive group, And if you take a subvariety and a finally generated subgroup, then their intersection looks like find the many arithmetic progressions. It's just find the many cosets of subgroups. So really here, what's happening is that your Abelian variety is something that has a group structure and an algebraic variety structure. And you're taking a sub-object in the variety structure and a sub-object in the group structure and intersecting them and saying you still keep structure. Okay? And that's kind of the same type of thing here. With a sub-variety is, well, something that's kind of like a group. Like I said, this also resembles the Stony model theorem, which is a fabulous theorem. It's kind of psychologically amazing. I'll explain that in a minute. But so you have some sequence of complex numbers that satisfies a linear recurrence relation. So like the Fibonacci numbers, or like it's something like an plus 5. You have an plus something is some rule, some linear combination of the previous handful of terms of the sequence. And for any such linear recurrence relation, if you just look at the spots where an is 0, it's just finding the linear arithmetic progressions. Now, one thing that's great about this result is every known proof uses p-adic analysis. So even though, as stated, this is a complex result, there is no complex proof. And it really uses, it crucially uses p-adic interpolation in a way that I don't know how else to do it. But anyway, it's the same type of, all of these results have the same type of flavor. And so let me state something that, maybe I should talk about it before removing these. Let me state things in a way that generalizes all of these. So our motivation, being number theorists, our motivation really came from Mordell-Lang. And our basic thought was, Mordell-Lang requires you to have something that has a group structure. But you really don't use inverses. You really just need to be able to compose things. You don't need to be able to invert things. So we just need to reinterpret, if we could just reinterpret this subgroup in a way that doesn't involve inverses, then we could formulate this much more generally. And so our reformulation is we're going to view the subgroup, this group of points, view it as the image of the origin under translation by all of these points. So translations by the points in the group, these are just some endomorphisms of J. And then we're taking the orbit of 0, like the image of 0, under all of these endomorphisms. And that's our replacement for this group. And then that's also something very similar to what we have here. Here we have the image of alpha beta under this collection of endomorphisms of the plane. X, Y goes to Fm of X, G and Y. Okay, so then, much more generally, you can ask if you have any variety, J, and you have a subvariety, and you have some point, then if you have finding many commuting endomorphisms, so finding many maps from J to itself, and they all commute with each other, just ask which ones are going to map this point into the subvariety, and does it look the same thing? Does it again look like finding linear arithmetic progressions? And so the good news is, well, so our result shows the answer is yes, and there's a slight generalization of our result. If the big variety is affine space, the subvariety is a line, and S is generated by polynomials in one coordinate at a time. And
the coset structure of a semigroup is not like partition in group cases. The cosets of a subgroup is a partition, right?
It can be much more, because the sub-semigroups can look much crazier. So we actually have a much more precise question, which involves, we have a much more precise question that's harder to formulate, which involves working inside Z to the end first, and getting a finely generated subgroup of Z to the end, and then intersect that with positive integers to the end, and then take a translate of that. And we think that that's what actually the truth is, that it's more painful. But this is all just for flavor, because we don't have a general theorem here. But so here we prove this, and our result, our result extends it once to affine n space. There's nothing special about it, too. The answer is also yes, that J is an Abelian variety, and S consists of translation, so that's the Mordell-Lang conjecture. The answer is also yes, if J is, well, the multiplicative group times the additive group, or just the plane minus a point times the plane. That winds up being equivalent to the Stony theorem. There are several other papers showing the answer is yes in many other situations, but unfortunately the answer is sometimes no. And we don't, we don't have a good understanding of when the answer is no. We have a few different types of counterexamples. They all seem to have some type of additive structure. But we don't want to throw away additive structures completely because word laying is all about additive structures. So we don't know a conjecture which agrees, which has the same truth value, yes or no, as this in all of these cases, and it isn't totally ugly to state. But we're very hopeful that there should be such a thing. And one thing that's really exciting to us is that the proofs in these, especially in these first three cases, the proofs are totally different from each other. So it would be fantastic to have a common proof to kind of explain why this similar phenomenon is happening in all these different settings.
But then you need a statement that might be true universally, instead of common proof.
Yeah, well, we don't know what the right statement should be. We're hoping that once we figure out enough cases, it'll sort of be clear what. And we proved in several other types of cases, but well, this future work.
Okay, can you go back?
Yeah.
So, what's the no sometimes? What's the flavor of the no?
Well, so the one example was in our case, if you had one of the maps being degree 1, if you have if f of u is just u plus 1, then we get examples. You get similar examples here. I mean, so they have J being abelian variety. So if you let J be just affine 2 space, and let your do all integer translation. Well, all integer translations. Yeah. Do translations by one in that direction and one in that direction. Those generate all translations. And then intersect with any crazy curve you like. You can, of course, get infinite, you can get strange infinite intersections. But then we have examples in powers of the multiplicative group that look a little different, but once we took a logarithm, they started looking similar. So there's a feeling that the examples all kind of resemble each other, but we haven't been able to get our fingers on what exactly is happening.
So do you have some positive results in high-dimensional homomorphisms? And so not rational functions, so what in one variable, but rather rational functions, etc., polynomials, etc. Is there?
We did things for powers of the multiplicative group. We have, in powers of the multiplicative group, we have some positive results. But that's still but that's all, the endomorphisms we looked at were all algebraic group endomorphisms, so they were kind of very special. Anyway, that's the flavor of this type of thing. Okay. Next result. So, polynomials over the rational numbers. So this is a result from an REU project 2 summers ago. So if you have a polynomial with rational coefficients, then the function you get, just x to f of x, is at most 6 to 1, maybe except for finitely many points. So, of course, there can be infinitely many points that have one rational preimage. There can, x squared is an example where infinitely many have 2 rational preimages. X cubed does not make infinitely many have 3, but there are examples where infinitely many have 3 rational preimages.
That's a polynomial, the notation you had with rational coefficients.
Oh, that's right. Yeah, this is a polynomial over the rational. That was a polynomial with rational coefficients. Any polynomial with rational coefficients. So there are examples where infinitely many rational numbers have 6 rational preimages, but there's no example where infinitely many rational numbers have 7 rational preimages. And so this is joint with Alex Carney and Ruby Horsch, who were Michigan undergrads at the time. I guess Alex is at Cambridge now, and Ruby's at MIT. Okay. And so this result, I don't want to say too much about it, but just to say, first of all, this is best possible. So you need this finite set. This finite set absolutely has to be there, because by Lagrange interpolation, you can say, I want a polynomial to map 3 to 7 and 5 to 4/3 and whatever. You can name finitely many conditions on your polynomial and use Lagrange interpolation to build a polynomial that does that. Okay, so you can make a polynomial that has 1,000 numbers mapping to 0 and 10 million numbers mapping to 1, but that's only going to be a finite set. And secondly, you can't improve the 6, and here's an example. There's an example of polynomial, which at least you'll believe this is something you could quickly determine if it's true or false. But I claim that these are actually identities. These are 6 different rational functions which have the same image under this polynomial. So for most rational numbers you plug in, you'll get 6 different values, and those 6 different values all have the same image.
Does it have any explanation?
Yes.
The 6 loss ratio?
So this is a twist of the Chebyshev polynomial. And the reason for 6 is because PGL2 of the rational numbers has a dihedral subgroup of order 12. Look at those. And actually this generalizes to number fields. For any number field, or in fact for any finely generated field of characteristic 0, you get the exact same result, and 6 gets replaced by the same type of thing. 6 gets replaced by the largest n so that PGL2 of that field contains a dihedral subgroup of order 2n, or equivalently, the largest n so that cosine of 2 pi divided by n is in the field. Okay, so cosine of 2 pi over 6 is a half. Right? It's not a contradiction. So, great. Okay, so how do we prove this? Well, we relate it to functional equations. So suppose you have a polynomial that's at least 7 to 1 infinitely often. So then you'll get, then you look at f of x1 equals f of x2 up to f of x7. This is some variety. It has finitely many components. And one of those components must still have infinitely many rational solutions. Infinitely many of these solutions must lie on some component. And there must be our hypothesis of being 7 to 1 says there's some component that isn't contained in one of these diagonals. So you get 7 essentially different, and it's only 7 to 1, not less. So there's some component of the subvariety which isn't in a diagonal and which has infinitely rational points. And it's easy to check that the subvariety is a curve, and so Baldy's theorem tells us that its genus is 0 or 1. And what that means is immediately in terms of functional equations, it means we get f of p, we get 7 different functions which are either rational functions or elliptic functions, such that f of p1 is f of p2 up to f of p2.
So far you haven't used the 7 to 7.
Right.
Just use 7. What did you use about 7 so far?
Nothing yet.
Just something to want it to off.
Right, exactly.
Even
And
1 to 1, even 1 to 1.
Right.
Yeah, okay.
I should have said the pi are non-constant. Anyway, so we get this functional equation. It's the same type of functional equation, except now f equals to p. And so then, then we solve each individual equation. We solve for 2 to 1 infinitely often. It's f of p equals f of q. We just somehow solve that. And then once you have 2 to 1, then we use Ritt's results. Ritt's results for the original equation, the f of p equals g of q. We use them to show how you could try to piece together multiple ones of these solutions to get a solution that's many more to 1. And I mean, I'm skipping a lot here, but just to give you some flavor of what goes into it, we also had to determine the Galois groups of a bunch of polynomials, compute some ranks of elliptic curves, or at least whether the rank is positive, and do some ramification computations involving Swan conductors and so forth. But ultimately, I mean, this was, once we turned it into functional equations, it's kind of, then we could approach the problem. Before it was written in terms of functional equations, we didn't know what to do. I mean, even saying this, even saying the Falking's theorem, when you know it has to have genus 0 or 1, it doesn't seem to help you very much because it's just a component. Like, we don't know how many components there are. We don't know their degrees. We don't have any formula for their genus. I mean, you can't immediately use Falking's, but what you can get from it is this reformulation in terms of functional equations. And then you can, then that's somewhere. So let me say, a possible, I mean, we connect this with some other things. So Mazur had a great theorem in 1977. This is what got him the Cole Prize in number theory. That any elliptic curve has at most 16 rational torsion points. And in hindsight, after our result, we can reformulate Mazur to say that if you just have a map between genus 1 curves, a non-constant map, the induced map on rational points should be at most 16 to 1. So the reason this is a reformulation is that maps between genus 1 curves have a, well, so if you have a genus 1 curve, and you, okay. If the first thing has no rational points at all, then the map is 0 to 1, which is the most 16 points. So that's fine. Okay. So assuming E1 of Q is not empty, pick a point and choose that to be the base point for your group plot you're going to impose on this genus 1 curve. So if you have a genus 1 curve and you have a point, you can use that to canonically build a group structure on the points on the curve. And that structure has this great property that when you take a map of curves, from genus 1 curves to genus 1 curves, that takes the origin of one group structure to the origin of the other, it's automatically a group homomorphism. Okay? So use your chosen point here as the origin here, use its image here to be the origin here. Then you get a group homomorphism, which means that the preimages of points in a group homomorphism are cosets of the kernel. So they all have the same size. That size is the size of the kernel, which is a group of rational torsion points on the curve. So this is the same statement, just written totally different. The good thing of writing it this way is that you don't need a group structure anymore. Like we've talked about torsion points without knowing what multiplication by n is. So that means that we can generalize it. Because our result, phrased this way, says that if you have a morphism from the outline line to itself, the induced map is at most 6 to 1 outside the finite set. Now we need this finite set, but I view this more as a statement about Mazur's result than about ours. I mean, I think the finite set deserves to be there. It happens not to be there in Mazur's result because maps between genus 1 curves have this extra rigidity from this group homomorphism structure. So you can't have any weird thing happening somewhere. Like all points kind of behave the same way. And that's totally rare. Like that's a very special thing about his situation. So, unlike the previous case, this time there are no known counterexamples to our outrageous generalization of this. So maybe, at this point, it's not known to be false. So conceivably, if you have any map between varieties, the induced map on rational points should be at most some constant to 1 outside lower dimensional locus, where the constant only depends on the dimension of the varieties. And in particular, it does not depend on the degree of the map. So there's some hope to prove this for certain classes of surfaces, because Zanier and Corbat, Zanier and Aaron Levin they've gotten analogs of Ziegel's theorem in some situations. And so you could hope to use that to prove something like this for certain classes of surfaces. So far we haven't been able to do it.
What about curves? Higher genus curves.
Well, they only have finite domain points to start.
Yeah, it's not C of D, though.
Yeah, but it's all in the lower dimensional
What?
locus. Oh, higher dimensional varieties? Do you mean higher genus curves?
Oh, you can just throw all rational points
Right.
in this lower dimensional stuff, right?
Yeah,
Well, maybe.
because right, in one-dimensional case, the lower dimensional thing is just any finite set, so that's our finite set that we excluded.
And also in higher dimensions, you are not interested in general type.
I haven't tried, but I would assume you can just prove this for general type, no?
I mean, use a design project or something that.
Oh, yeah, you might be able to use that to actually prove this for. Yeah, that's interesting stuff. We were able to use the length. I mean, if we use length conjecture on rational points, I mean, we could bound the finite set in terms of the degree of the map. And that's not that hard. But anyway, that's a conjecture, and that's involving degree also. So anyway, that's okay. So the skip from so that was about injectivity. That was about how much a map can fail to be one-to-one. Now I want to talk about images. So Mazur's theorem stated another way. So if the talk was too technical for this, I guarantee you everyone can understand. I have to admit that I presented this result this way to a group of number theorists, and Andrew Graham will actually started laughing. But I don't think he objected. He just found it funny. But anyway. If you have a polynomial degree 3 with rational coefficients which has no multiple roots, as soon as it takes at least 8 square values, it must take infinitely many square values. So this is because I'm talking about rational points on the curve y squared equals f of x. And basically, Mazur said you can only have so many torsion points. As soon as you have too many points, one of them must be non-torsion, and then you get infinity. Okay, but this is a totally, I mean, even if you didn't know Mazur's theorem, you can accept this as being true, which it is, and then, okay. So, very recently, as in, I mean, this was announced in a talk last week, Montel presented an amazing result, that for any fixed degree, if you look at all square-free degree D polynomials, most of them don't take any square values at all. And this, I love this, because this is something that, like, you can explain this, as soon as someone knows what a polynomial is, almost, you can explain this to them. And this is really, this is great.
What does proportion mean here?
So he orders the polynomials based on the largest absolute value. Well, sorry, he makes them be integer. He makes them be integer polynomials. He orders them based on the largest absolute value of any of the coefficients, and he takes the limit as this largest goes to infinity. And so, and it was even better because I mean he gets some bounds probably range too.
So you're saying you have a countable set, and I'm talking about proportion. First you have to decide the finite filtration of it is, and then you take the proportions and the limit.
Exactly.
You're taking this largest coefficient to be the filtration.
And the expectation is that 100% of them don't have square values. And he said that once his degree is at least 20, he can prove that more than 99% of them don't take it. But it was already, I mean, before him, it wasn't known, well, not even about, I combined two results. I'm sorry, more than half of them don't take any square values. I'm sorry, I combined this with a, he had previously proved a positive proportion for degree 3 with his student Roel Schenker, but his recent result blows that away. He actually showed at least half for any degree, and at least 99% for a degree at least 20. So it was an awesome result. Vaulting's theorem says, I mean, Wardell conjecture stated in accessible terms says if you have any square-free polynomial degree at least 5, then you only get 5 infinite square values. So now we're not talking about most, we're talking about the weird ones that have a lot of values, still don't have many. And then there's a conjecture that really the weird ones don't take many. That there's some uniform bound. So just to state the example of this particular case, there is a degree 5 polynomial, square-free degree 5 polynomial that takes 321 square values. People have looked and can't beat it. And people believe that there is some record. People believe that this doesn't go to infinity. Wow. People have stated conjectures which imply that. I'm not sure. I've never been sure if Caparozzo, Harris, and Mazur believe this conjecture.
Is this finite bound that Paul's constructive bound?
No, but that's exactly what this conjecture.
The finiteness of homogeneous abstract points, is that a constructive finite number or just an abstract finite number?
Well, it's not knowing that there's a uniform bound.
No, other than that, just the, if you have a finite, I mean, if you have a set of the proof that shows the finite set of integers, then an estimate is the biggest integer in that finite set. It's not constructive. So, but if you,
I think for a particular curve, I think Paul's proof is constructive. But if you try to maximize over curves, then the maximum goes off to infinity. But anyway, so this raises a more general question. What happens if instead of looking for square values, you just look for common values between two polynomials? So instead of f of x equals y squared, look at f of x equals g of y. And so this is what we did this summer. Those are the undergrads, and then there are...
you're missing one because there were 10 names on the first slide, and that's only about 10 letters.
There are 11. Oh, I'm the Z.
Yeah.
I'm the Z. So, okay, so these are
the 11, only 10 letters.
there are 7 undergrads, and then my former student Alex Carney, who was already pictured, he helped, and then my former grad student Ben Weiss, who's the first W, also helped. So those are the
Town Village.
Yeah.
There's our Town Village.
Indeed. Okay. Yeah, she's right. She actually, for a while, she thought she was going to be the first of this crazy list. Anyway, but then Alex followed. Okay, so just to give you some sense of what I mean by saying that we've classified all instances where this equation, f of x equals g of y, has infinite solutions in a number field. What I mean is there are some easy ways to build new solutions from old solutions, and in the essential solutions, either you have one of the polynomials being x to the n, and the other is something explicit, or one of the polynomials is a Chebyshev polynomial, so the thing taking cosine theta to cosine n theta, and the other, well, we can kind of say something about. Or there's this weird case, which isn't so weird. I mean, these polynomials in some sense have come up over and over and over in lots of different settings. I mean, for instance, these are crucial. This is the engine for Bellier's proof, or Bellier's theorem, that how do you recognize when a curve is actually writable over a number field is when it emits you have a curve over the complex numbers. You can write it over a number field if and only if it has there's some rational function on it that has at most 3 poles. Or sorry, it has at most 3 branch points, at most 3 critical values. And the engine in Bellier's proof really was this. He reduced to the case of 4 and then got from 4 to 3, right, like this. But it's just, this example has come up in many, many places. And then also we get a bunch of sporadic examples, which we can explicitly write down. Oh, oops, I said if and only. Well, this and on an explicit list. Everything else is if and only if. This last one, we can explicitly list. So those are just some comments about the Chebyshev case, that we can actually say something about how many G's there are, and relate them to some geometric condition. I don't want to spend too much time on that, so we just go on. Okay. So next time. Okay. Complex analysis. So complex analysis for non-analysts, if I can be allowed to do this. So an entire function is just a function given by a power series that converges everywhere. A meromorphic function is the ratio of 2 entire functions. Don't divide by 0. And then there's Descartes' theorem, which is awesome, 1887. If you have a non-constant polynomial with 2 variables, then when does it emit a parameterization by meromorphic functions? Like it emits, there are non-constant meromorphic p and q, so the f of pq is 0, if and only if some irreducible factor of f gives you a curve of genus 0 or 1. So, great. So, solution to the functional equation if and only if genus 0 or 1. Now, Faulty's theorem is almost exactly the same theorem. You have 2 variable polynomial of the rationals. This equation has infinite solutions in some number field if and only if you get an irreducible factor defining a curve genus 0 or 1. So, the last part is exactly the same. There's this amazing formal similarity. And this is not an accident. I mean, how do I say this differently? It's not actually known that this is not an accident, but it's known that there's a whole slew of things related to this that seems to be true. There's these incredible parallels between results in complex function theory and number theory. There's a precise dictionary for going back and forth. But so far, there are no theorems that actually say you can go back and forth. It's like the statements of the results carry over, but you need different methods of proofs. But just to give a little sense of that. Okay, so why am I talking about this? Well, because I want to talk about Never-Limit theorem. So there's this theorem of Never-Limit, which is, when I first saw this, I'm still feeling the shock when I first saw this result. So if you have 2 non-constant meromorphic functions, if they have the same preimage as each other at each of 5 different complex numbers, then they're the same.
So the preimage sets, possibly infinite sets.
Yeah. And I don't count multiplicity here, just sets.
Just sets.
And so people over the past almost 90 years, 87, something. 87 years, right. People have studied, there are a lot of people, there's a huge literature actually, kind of disturbingly large, on what happens when you generalize from equality of preimages of points to equality of preimages of sets, so finite sets. So you sort of take a union of a few of these, and then, but don't say which alpha they're coming from. Just tell them the same preimage of the union, same union of the preimages. So there's one known way to get to actually make this happen, and that's if you have a functional equation. So if f of p is g of q, where f and g are some rational functions, you can just take pre-images of any point on both sides, and you get P inverse of F inverse of gamma is Q inverse of G inverse of gamma. And then F inverse of gamma is some finite set, and G inverse of gamma is some finite set. So you get a whole bunch of pairs of finite sets, so the pre-images of 1 under P is the same as the pre-image of under Q. Now, a possibly crazy question. So this, I should say, this is not a, I mean, this is not in the literature. Nobody has asked this before, as far as I can tell. And I'm a little nervous that conceivably people have a good reason for not asking this, but I couldn't find one in the literature. So maybe this explains all examples. Maybe this explains all examples where two meromorphic functions have the same pre-images at infinitely many pairs of finite sets, or even just at finely many but enough pairs of finite sets. And so what I can say, so using the methods of this paper I wrote with Bob Beals and Joe Weatherall, actually Bob is in town, he works at Renaissance. But using the methods from our paper, I can prove that the answer is yes, that P and Q are rational functions. In fact, if you have rational functions, all you need is two pairs of sets where these agree with multiplicity. But you certainly get the, I mean, multiplicity can only come from critical values of P or Q when rational functions only have finitely many. So as soon as you have equality of enough pairs of sets without multiplicity, you'll automatically get some with multiplicity. And once you get two with multiplicity, then yes, there actually is automatically a functional equation explaining. And this is not so satisfying, but the best that we can prove so far, this is again with my former student Ben Weiss, we can show it's yes for meromorphic functions if both of these polynomials, if the characteristic polynomials of all of these sets, or at least sort of in total have many fewer critical points than they deserve to have. Right, so any polynomial deserves to have like its degree minus 1 number of critical points. We need these in total to have roughly half that. And if that happens, then we can prove that yes, once you get this, then you automatically get a functional equation explaining. And so here, let me just be quick about this. The idea is that we use Never-Lina's second theorem. I mean, well, we use all of Never-Lina theory, but the engine is Never-Lina's second theorem to say that when you get equality of one pair of sets or of many pairs, it's just a more complicated statement. And if these things have roughly half their share of critical points, then we automatically get some functional equation coming out. And then the earlier work, actually all of the earlier work, all the earlier work says that we can solve this functional equation. Like we know all solutions to this functional equation. And so that says by combining these two, it says we can build lots and lots of pairs of sets, S and T, so that if P inverse of S equals, well, so the P inverse of S never equals Q inverse of T. Okay? Well, what I suspect is that most pairs of sets, S and T, have this property. That there are no non-constant meromorphics of the P inverse of S equals Q inverse of T. We can't prove that because our condition is too restrictive. Like, typical polynomials have their full share of critical values. They don't have half their share. So this is the closest we can get to proving that, but that's what seems to be true. And I mean, I'm excited that we get this connection to functional equations, and then by using functional equations, we can get something new. Okay, so just to finish up, let me say how did we do this? How did we solve this equation? So I should say this, I mean, the work put together for this is about 200 pages. So these two slides are a little concise. But so basically, so we use Picard's theorem, and we use the fact that if a curve has one meromorphic parameterization and it has a minimal one, to say that this problem is really the same as saying when does f of x equals g of y have a component of g0 or y. Okay. So first we deal with the irreducible case, and then the reducible case is kind of a new type of beast. So in Rick's work, he only ever had to face the irreducible case. So he was awesome, so I wouldn't doubt that he could have done the reducible case somehow. But in fact, he only ever needed to deal with the irreducible case. Because in his work, the reducible case his hypotheses made the reducible case be easy. Okay. But we are following Rick whenever possible. So the idea is that you can write down the genus of this curve if it's irreducible. The crucial thing with being irreducible is that this curve, it's really, even if there's f equals g, and irreducibility means that our curve is the fiber product of these two, which means that we can understand the ramification in this map from the ramification in f and g, and then use Riemann-Hurwitz to get a formula for the genus of x in terms of the ramification in f and g, which just means what are all the multiplicities of all the roots of f of x minus 3, f of x minus 4, and so forth. So it's a collection of, so if for every lambda you tell me the multiplicities of the roots of f of x minus lambda, g of x minus lambda, from that data we have a formula for the genus of x, or genus of f of x equals g of y, and then we use that. This is why, I did a back of the envelope calculation today to say that, even though it's elementary, there are better and worse ways to do this. So my student Ben Weiss, he wrote what I thought was a great thesis, in which he spent 80 pages doing a hard case, what seemed at the time to be a really hard case of this. So this was really a big advance. That was reduced to 3 pages during the summer, but then the solution of this took 120 pages, so the calculation would be 3,200 pages by the earlier approach. But, what I'm saying is that, even though it's totally elementary, you still need to do things in really the right way. And that was, the students, well, Hal in particular, did fantastically well at solving these equations to write down all the numerically plausible factorization types. And then we kind of use methods that Riemann developed to go back from that and build up the polynomials. I don't want to go into that too much. Okay. So what about the reducible case? Well, usually to get from irreducible to reducible, you just factor. But that doesn't work here because factors of f of x minus g of y are going to have cross terms. They don't look like f of x minus g of y anymore. So you can't piggyback off the irreducible case to get to the reducible case. So instead, we pass from the decomposable case to the indecomposable case, meaning just composition of polynomials. We write f as a composition of a bunch of lower degree polynomials. Here we used a lot of group theory. So one result we proved was that we can explicitly write down all indecomposable polynomials for which this Galois group, the Galois group of f of x minus t over c of t, is not Sn or A. So this is the monotony group for the inverse function of f. And this, we really heavily built on all this previous work, and Fried's paper had a Stony Brook address, actually. There is a local connection. And as a corollary, we can explicitly write down all indecomposables, all pairs of indecomposables, so that f of x minus g of y is reducible. Which means, based on knowing the irreducible case, we can do most of the 2 indecomposable case. When this is reducible, we deal with it directly. Now, since an expert is in the audience, I should maybe say a previous paper, a paper by Casanova and Covania had claimed to do this, but their result is completely false, and their proof is unsalvageable. There are lots and lots of counterexamples to their result. So we couldn't use their technique. So we really actually had to basically prove this from scratch. So that's why we proved this result. But then later in the proof, that lets us get started. That lets us handle the indecomposable case. Then essentially, in a nutshell, what we did is we had some decomposition. We have f is like from f1 equal to f2 converted to f dot g is similar. So we kind of factor f as f1 composed of f2, and we factor g the same way. And we take the minimal piece, the smallest piece that gives us something reducible. So we took the smallest reducible piece, which means the last indecomposable we put on is the thing that's causing reducibility. And then we use the fact that we had control of its monotony group. We had control of this Galois group to say from control of this Galois group, well, we kind of worked our way up. So there's C of x, C of f1 of x, C of fk of x, C of fk minus 1 of fk of x, and so forth. So something comes to field extensions, the same things on the other side from y, and we just take composita of these field extensions. Everything in sight has to have genus 0 or 1, because the genus can only go down when you map down. So we go to the very last piece, which was causing the reducibility. So everything below it is irreducible. And then we take this compositum of the next to last guys on both sides, use this Galois group to control this Galois group, use this Galois group to control this one, play these two off each other using reducibility, and kind of use this as a crutch to connect the two sides, which then puts us in a situation where we can make the ramification arguments. So that's, that's a 30-second description of the AEK argument, but that's kind of the idea. So we absolutely needed to know not just the reducibility at the bottom, but exactly what the groups were at the top. Because reducibility is just a nightmare. I mean, we still don't know how to deal with reducibility. We kind of just sidestep it. We deal with it just enough. Okay, so just as a summary, so we solved this function, we solved several instances of this equation, and we applied them to find the intersection of orbits of complex polynomials, so the other results. And I can say that there are several other things that have been done using rich results as well. So I just mentioned two more things using rich results. So a complex dynamicist, Din and Fedor Pakovich, I don't even know how to describe him. He's in many areas. They found all pairs of complex polynomials which have the same pre-images of two infinite compact sets. And this crucially used rich results in really a different way than what I've been describing. And then there's a very recent long Annals paper by Alice Medvedev and Tom Scanlon, who are two logicians, where this is algebraic geometry. And they say, what are all subvarieties of AN that have an endomorphism which is separated, which is like a univariate polynomial on each component. And they just write them down, do a description. And amazingly, they do this by combining the super results in model theory by Zoe Chadzidakis and Uli Rashkovsky. They use that basically to reduce to the case of the affine plane, and then they just write off what the component functions are, and they quickly reduce to an instance, they reduce to semi-commuting polynomials. The f of p is p of q. And then they say, okay, let's solve that, and then we get to solve everything. So they also give applications to logic, and there are several other applications as well. So that's, I hope I've convinced you that this is something that really comes up in places. Thanks for your attention.
Questions?
You had some results involved in Chebyshev polynomials, some formulation. Do you have any similar results for rational maths involved in lattice? Yeah.
I totally believe this. So there's a much better version of the 6-to-1 result, which says, if you look at polynomials which over any number field,
this is a Colloquium. Why don't you say what the question is?
So maybe you should go with the result.
Well, okay, so he wanted to generalize from Chebyshev to lattice. So it's right. So Chebyshev are, and the reason they're special is because these are the map on x coordinates induced by z goes to z to the n on the circle. So these are a shadow of a group homomorphism, and there are lots of results in dynamics where kind of all the special rational functions are things that either they are group homomorphisms or they come from group homomorphisms in this way. Yeah. And so the expectation, so there's a much better version of our 6-to-1 result. There's a result that says, what we really prove is that over any number field whatsoever, if you have a polynomial that's more than 6-to-1 infinitely often, it has to be coming from either x or the n or Chebyshev. Like, those are the only sources of more than 6-to-1ness over any number field whatsoever. And if you go to rational functions, certainly you get lattice maps. These are the map on x coordinates induced by some endomorphism of an elliptic curve. In some cases, you can quotient by a larger group of automorphisms than just plus or minus 1. But basically, they're shadows of homomorphisms of elliptic curves. You get those as well, and I mean, we're really hoping for a rational function analog of our 6-to-1 result. I mean, that would imply Maser, for instance. I have a student, I mean, it's just hard. I mean, so I have a student who's Sejun Liu who's working on this. I think he'll be able to prove it for Laurent polynomials, but right now at least it's kind of scarily difficult. So I'm a little daunted, right? I mean, right now we just don't know how to get far into the rational function territory for that. For the f of x equals g of y, I mean, Tao did some initial computations and some particular, under reasonable hypotheses, and Lattice functions jumped out. So it may be, I mean, that was an interesting thing for the f of x. Oh. That was an interesting thing, but essentially all the examples came from group homomorphisms. There. Right. But except for this one weird thing and logically things, you're getting group maps. And I don't understand why that happens. I don't see, this is not dynamics. I don't see why the group maps are coming up. I mean, to us, they came up just because the ramification was consistent with something, but that's a weird explanation. But when Tao did things in the case of rational functions, again, we started seeing lattice coming up. So it seems like there's some general principle happening that when the genus is small, the reason is because there's a group map.
Oh, there's too much notation. So where's the I mean, just invert these endomorphisms of the torus pushed down to the sphere. That's my miraculous examples. Chevy Chess examples, I don't know what they are.
Oh.
Characterized. But wait. Give me some statement that picks out those mappings.
Oh, sure. That's just, that's in Miller's paper on lattice maps, right? So it's, if you have like, so the question is, when can you have a one-dimensional algebraic group, and you have an endomorphism of one-dimensional algebraic group, when can there be, I shouldn't call it, when can there be a projection P1 so that...
I want to know that take the rational maps that you get this way on the sphere, that which of your considerations discovers these are special? How do these types of maps fit into some of the theorems you're saying?
So all F's which come this way, come from an endomorphism of one-dimensional algebraic group, all of these F's are showing up.
In what way? What's the statement?
Well, there's that
I can't read that. I mean, tell me in words. No, I don't want. Just tell me in words.
Well, then if you have an F, then you have F. Then F of x, there will be g of y's. So that F of x equals g of y has genus 0.
What?
If you have an F like this, there will be rational functions g, so that F of x, so that the curve F of x equals g of y is irreducible. Well, genus 0
F of x equals g of y. That's too fast.
Well, we're looking at F of x equals g of y. We want to say when does F genus 0 or 1, and I'm saying always if F is coming from a group homomorphism. I mean, always, if F comes from a group homomorphism, there are G's for which this happens. And amazingly, there are essentially no other examples except for
the G's are what? What kind of maps are they?
Well, these are the things that are solutions to these palette. I mean, those are ugly. They're solutions to these palette points, so we have some control on how many branch points they have. I mean, how many pre-images of plus or minus 2 that have odd ramification. But that's all we have. Like, I don't have a nice description of those G's. I mean, well, that's all I have. I mean, I'm not happy with the description of G's. I wrote them down, I computed them for degree up to about 100, and I mean, it started taking longer and longer to write them, and I couldn't see any nice pattern or anything about them.
Any further questions? Well, let's make like again.